Hey everybody! So this lecture is going to be on viewing and projection, specifically in the context of rasterization. So by now you're familiar with the basic setup for rendering, which consists of some scene that we're trying to render, and a view that we're trying to render it from. And our goal is to compute some image of our scene defined by an image plane, which we can typically think of as lying somewhere between our view and our scene. And by now you know that there are two popular approaches for doing this. Ray tracing should be fairly familiar to you at this point. The basic idea is that we iterate over the pixels of our image, and we look up the intersections of each corresponding ray with our scene. Ray tracing is becoming increasingly popular, but is still mostly used in film and video applications that don't have to run in real time. In contrast, most interactive 3D graphics are rendered using rasterization, which works by iterating over scene geometry and projecting each element of the scene onto the image plane. So in both cases, we're mapping geometry to pixels, but in ray tracing, we do this by iterating over pixels, and in rasterization, we do this by iterating over geometry. So rasterization is sometimes called the forward approach because it transforms from input geometry to output pixels. And ray tracing is sometimes called the backward approach because we're iterating through output pixels to look up input objects. So this lecture is going to be about how to map scene elements to pixels in rasterization. So at this point you've learned about how a scene graph represents transformations from object coordinates to world coordinates. Now in assignments 1 and 2, we used a kind of forward rendering, but in those cases we measured world coordinates in terms of pixels on your screen. By contrast, in 3D graphics, world coordinates don't even have the same number of dimensions as screen pixels, so clearly some additional transformation will be necessary, and at least part of that transformation will be a projection. So in this lecture, we're going to factor that transformation into a few different pieces that will let us control different aspects of rendering, namely the view matrix, which controls the location of our camera in a scene, the projection matrix, which aligns points with their projection on our image plane, and the viewport matrix, which maps our image plane to the pixels that we ultimately display. So we've got a bunch of different transformations and coordinate systems here, which can get a little bit confusing, and it can make what we're doing here seem a lot more complicated than it is. So before we get into these transformations, let's walk through what the rendering pipeline looks like if we just replace all of this with the identity matrix. So our setup is that we have some 3D scene, generally consisting of some geometry made up of triangles, and we want to map this scene onto a 2D image plane. And let's say that the image plane is the xy plane defined by z equals 0. We'll see how to choose a different image plane later, but this will be our standard for now. Now let's say that our triangle has vertices A, B, and C. If we're using the identity matrix for all of our transformations, then we aren't really doing anything to the coordinates of these vertices. So in this case, we'll just use the x and y coordinates as screen coordinates and ignore the z coordinate for now. Now this is almost the same as zeroing out the z coordinates, which would correspond to an orthographic projection of the scene. But carrying the z-coordinates through the transformation ends up being really important when it comes to rendering lots of elements, because it's common for multiple triangles to project onto the same pixels. And when this happens, we want the geometry that's closer to our camera to obstruct geometry that's further away. And in order to make that happen, we need to keep track of each triangle's depth in our scene. More generally, carrying the z-coordinate through lets us keep our projection invertible, which will also let us do things like look up the geometry corresponding to some query pixel, which can be really useful, for example, in graphic user interfaces. Okay, so now let's shift our view a bit and look at what's going on from the perspective of our computer screen. Remember that the xy plane is our image plane, so the viewer is basically looking down the z-axis, and our projected vertices are going to form some triangle in the image plane. So our question now is, how do we go from this triangle to an image? And the answer is rasterization. And if you're wondering, wait, I thought all of this was called rasterization. Well, the broader rendering method referred to as rasterization gets that name from this key step in the process. Yes, that can be a bit confusing, but it doesn't seem to cause too many problems in practice. Probably because of all of the steps in rasterization, the actual rasterization part tends to be the most standardized, and so people don't usually write their own code for it. So how does rasterization turn triangles into pixels? Well, Steve has a more in-depth video about this, but the basic idea is that you start in the corner of the screen, then you iterate over the pixels row by row, and every time you reach an edge, you start painting pixels until you reach another edge. And then you keep doing this process until you've painted the entire scene. And that's all it is in its most basic form, but Steve will talk more about this in his lectures. So with that process in mind, we can go back to our pipeline transformations and look at each of them as a way to further customize the basic approach that we just described. So let's start with the view matrix, which controls the position of our camera in a scene. Which brings us to an interesting question. Where is the camera located in the process that we just described? Well, it turns out that with orthographic projection, this can become something of a philosophical debate. because we often describe the center of projection as the point where projection lines intersect. But orthographic projection lines are parallel, so where does that leave us? Well, one interpretation is that orthographic projection is the limit of moving your camera very far away. But here's where things start to get kind of trippy, because the same exact projection is also the limit of moving your camera very far away in the opposite direction, which almost seems like a mistake at first, but it's not. In fact, it's the reason behind one of the most famous modern optical illusions, the spinning dancer. And if you haven't seen this before, the idea is that this is simultaneously an animation of a dancer spinning clockwise and a dancer spinning counterclockwise at the same time. Now, once you see one interpretation, it becomes very difficult to see the other. But if you close your eyes for a few seconds and look at it again, you may see the other way around. And if you ask a room full of people, you'll often get mixed answers. Now, the dancer GIF was the original version of this, but it works with basically any silhouette rendered with an orthographic projection. So of course, I have to show this example I found with a cat. Anyway, returning to our original question, this poses a bit of a problem because how do we move the camera if we don't know where it is? Well, we can generally assume that wherever our camera is, it's fixed relative to our image plane, which offers another interpretation of orthographic projection as being a bit more like a flatbed scanner. So if we want to move our camera, we'll just move our image plane. So how do we move the image plane and therefore our camera? Well, what we really care about is getting the same image that we would get if we moved the camera. And in this regard, moving the image plane up, for example, will give us exactly the same image as moving our entire scene down. More generally, applying any rigid transformation to our camera is the same as applying the inverse transformation to the world. So in terms of our scene graph, the view matrix sits just above all of the modeling matrices for our different objects, and it transforms from world coordinates to what we call eye coordinates. And the big thing to remember here is that the view matrix controls the position of our camera, which we can move by some transformation t by multiplying our view matrix by the inverse of t. Okay, so that covers the view matrix. Now let's move on to the projection matrix. We've seen orthographic projection, so now we're going to focus on how perspective projection works. First of all, since we're applying our projection matrix to eye coordinates, we can assume this standard configuration, where our camera is located at the origin, looking down the z-axis. Actually, I think in OpenGL, the standard might be that it's looking down the negative z-axis, but those are the main two standards. So let's say that we have some point P, and some image plane, parallel to the xy plane, defined by the equation z equals some distance d from the origin. Now we can describe the projection p' of p onto our image plane as the intersection of the eye ray through P with our image plane. So right away, we know that the z-coordinate of this projected point must be equal to d. Because remember, we defined our image plane with the equation z equals d. So the question is, what are our projected x and y coordinates? Well, for this we can use old school similar triangles. We have one triangle defined by our point P and its projection onto the z-axis, and we have a second similar triangle defined by P'. And we know what the base length of both triangles is. All we need is the hypotenuse of the smaller one. So applying the rule for similar triangles here, we multiply the point P by d over z, which gives us dx over z, dy over z, and d. And at this point, if you're thinking, hey, that kind of reminds me of homogenization, well then you're onto something there. Because another, albeit less common, name for homogeneous coordinates is projective coordinates. And we can represent perspective projection in homogeneous coordinates as a simple matrix multiplication. So this is super convenient, but our projection matrix is different from our orthogonal matrix in one important way, which is that it has this column of all zeros. And that makes it singular and uninvertible, which on the one hand kind of makes sense. I mean, after all, this is a projection. But this rank deficiency means that once we have homogenized a point, we have no way of knowing what its original coordinates were, which is problematic because, again, we may have multiple objects that project to the same pixel, and we want to be able to identify the closest of those objects so that we can have it obstruct the objects that are behind it. So what can we change to bring depth back? Well, notice that we aren't really using this third row of our matrix for anything right now. The output, d, doesn't even depend on our input, x, y, z. So let's see if we can use it to keep track of depth instead. Now we can't actually change the third row of our matrix to turn this d on the right side into a z, because that would require a z squared before homogenization. And we can't change these two entries of our matrix without making our output z dependent on our input x and y coordinates. So we're left with these values to change, and the goal of carrying useful depth information over to the right side of our equation. So let's call these values a and b. And if we multiply this through, we get a plus b over z on the right side. So now we're going to use the following strategy. We're going to pick a range of depth values in our scene, bounded by a near plane z equals n, and a far plane z equals f. And we'll set a and b so that our depth is going to be -1 at the near plane and +1 at the far plane. So the first thing we'll do is we'll make our near plane the image plane so that we can get rid of one of our variables here. And now we have two equations with just two unknowns, a and b. We can use the first equation to express a in terms of b, substitute that into our second equation, use that to solve for b, and finally plug that back into our earlier equation to solve for a. This is a fairly straightforward exercise if you want to try it yourself. Now I do have to add a note here that OpenGL uses the convention that cameras look down the negative z-axis, which means a and b end up being the negative of what we derived here. So do be aware of that. One useful bit of flexibility that we have in our choice of projection matrix has to do with the selection of the near plane, which is analogous to picking the focal length of our camera. And as with real cameras, the selection of focal length is what determines the field of view. So in particular, a small near depth will correspond to a wider field of view, while a large near depth will create a more narrow field of view. So you can keep this in mind if you want to go for a look that's a bit more like a wide-angle lens versus a telephoto lens. Now, one way to visualize the effect of a projection matrix is as a transformation that maps a specific region of I-coordinates, which we call the view frustum, to a 2x2x2 cube centered at the origin. We call these new coordinates where the cube is defined normalized device coordinates, which is a totally lame name, but whatever. So the next thing we do in normalized device coordinates is called clipping, which is where we throw away any geometry that's outside of the 2x2x2 cube. So anything that's outside of our cube in the x and y dimensions, you can think of as just being off screen. But we also clip in z, partially so that we don't render things that are supposed to be behind the camera, and partially for precision issues, which I won't get into right now. So that's the projection matrix. It transforms from I-coordinates to normalized device coordinates, and remember that by moving the near plane, you can change the camera's field of view. So then the last of our transformations is the viewport matrix, which is also the simplest. Its role is to map normalized device coordinates to screen coordinates, which is simply mapping one square region to another. So here I actually took one of Steve's old slides describing how to generalize this map, but you should also be pretty familiar with it from all the way back in assignment 1. So that's the viewport matrix. What comes next? Well, once we've reached screen coordinates, our situation looks pretty much identical to the process that we described at the beginning. So at that point, we're ready for rasterization. And so at a high level, that's it. The rest is mostly interpolation and shading, which are both important, but you'll learn more about those in some of Steve's videos. So with that, thanks for watching, and see you in section.